Thank you. Hello. Today we are here to talk about process injection and how we can move out from standard process injection pattern to try to limit detection by standard security solution. Let me introduce myself. So my name is Yoann. I'm 27. I'm a security auditor from Wavestone for almost 5 years now. So I'm dedicated to large-scale red team operation, and I'm also performing some development of internal tooling, mainly on the malware development and all things linked to Cobalt Strike and C2 development. So I've done malware development workshop at Dequeker last year, and I also did a speak at Le Hack in Paris. So let's dive into maybe process injection. So process injection is a subset of malware development techniques that allow an attacker to inject a malicious payload into a legit process. So these techniques are kind of interesting because they allow the attacker to hide its payload in a legit process. So if someone is just looking at the process tree, he will not see the malware.exe executed, but only the legit process. Likewise, it's kind of interesting because for access persistency, because the payload will be running as long as the injected process does. So if you inject your payload in teams.exe, you will be set up for the day. Standard process injection pattern is usually performed in 3 steps. So, for example, you have the initial process, so the legit process you want to inject to, for example, notepad.exe. So if you look inside the memory of this process, you will see all the junk related to the process. And you will have some free space. This free space is usually here due to some memory alignment. And because Windows only allows the creation of memory space of 4 kilobyte, kilobyte. So this free space would be at least 4 kilobytes, so it's not enough to write any interesting payload. For example, a Cobalt Strike beacon is between 80 and 100 kilobytes. So the first step when you do process injection is try to extend this free space, and this can be done using allocation primitives such as the virtual alloc eggs Win32 API that allows to extend the memory space inside the process. Once you have extended this memory space, you can write your malware inside it with the right primitives such as the write process memory, and everything is set up. The last step is to compile the process to start executing your malware. So you can do this with an execution primitive such as create remote thread that will create a new thread in the targeted process starting at a specific address. So you can compile the process to start a new thread to execute your malicious payload. And you will have successfully performed a process injection. So this pattern is really reliable. It works every time. The problem is that it's kind of old, and all security solution knows about it and can recognize this pattern. So if you try to do it against a standard security solution, you will be flagged, your process will be killed, and nothing will happen. So the goal here is try to move out from this standard process injection pattern and see how we can change the allocation and the execution primitives to limit the detection performed by the security solution. So we will see different techniques. We'll see why the standard process injection pattern is flagged and how we can move out from this. So the first thing is the memory allocation. When you are doing a process injection, memory allocation is a mandatory step, and we have to do it without raising specific detection. So when we used virtual alloc, what we've done is that we have created a new memory section in the process memory space. So when the process is started, it will load all its DLL, which will create a lot of different memory sections, and all sections will be attributed with with the state, so it's committed or reserved, the size, the protection, so read, write, execute, and the file related to this section. So, for example, you have on the third line memory section of 580 kilobytes with a read execute permission and related to the user 32 DLL. So the OS, the operating system knows why this memory section exists and how it is used. When you use virtual alloc, you can choose the size and the protection, but you can't map a file to it. So if someone look at the memory space of the process, he will see a memory section that is not linked to any file, that is not known by the operating system, and that doesn't have any use case known by the operating system. So it's kind of hard. What we can look at, it's a load library Win32 API. This API is mainly used to to dynamically load a DLL into a process. And when loading this DLL in the process, the operating system will map all the DLL information in the memory. It will create a section, set some protection, and link it to the DLL file. So this is kind of interesting because by loading a DLL, the edge case is that we are creating additional memory in our process. We are setting some specific protections, and we are linking it to a file. When we link a memory section on a file, it's what we call a backed memory space. So with virtual alloc, we have an unbacked memory, and with load library, we are creating backed memory. So the question is, why can't we use virtual alloc with a backed memory? When we are using a load library, is not using a virtual alloc. It's using NT-map view of section API, and it's because the use of this API that the OS knows that the section is related to a file on the file system and specifically on the DLL. So the problem with this is that when using NT-map view of section, you are raising a kernel callback, a kernel event that can lead to a potential detection. So you have two cases. You can have backed memory, but you have a kernel callback, so it's an image load event, or you can use unbacked memory. So which one is better? It depends on your use case. If you use unbacked memory and you start doing a lot of syscalls from unbacked memory, security solution will start raising some events and you can be flagged. But if you are starting to load several different DLL on your process, for example, if you're starting to load 10 or 20 different DLL in notepad.exe, the EDR will also see that something odd is happening. So you have to choose depending on your use case. So now we have seen about load library. The question is how we can compel a process to load a specific DLL, because load library doesn't allow a remote process to load a DLL in another process. So what we will do is another process injection using virtual alloc. So it's been what we will do is that instead of creating a memory space of 20 or 100 kilobytes, we will create a free space of 4 kilobytes, which is the minimal size of memory allocation we can do on Windows. Because it's a minimal size, a lot of security solution doesn't raise any event about it. We can also use some code case, so some free space already existing on our process. The only thing we have to have is enough space to write the path of the DLL we want to inject. Once we have written our DLL path in the remote process, we can use the create remote thread to start the execution of load library inside the remote process. With as parameter the DLL path we have already written in the process. So with that, we can compel a remote process to load a specific DLL and create additional memory in this memory space. So we are doing all of this to be able to write our payload in the remote process. So once we have created the memory space, we have to choose where we will write our payload. If you remember, when you are using load library, you aren't able to choose the section memory size, neither the protection. So some DLL have interesting sections with read-write execute privileges, rights. Sorry, but those DLL are not common. So most of the time you will have only section with read-write or read-write, read-execute, but you will not have read-write execute. So what we will have to do now is choose a section where you will change the protection and write to malware. The best section is the .text sections, because this section is already in read execute. So you can change the protection from read execute to read write, write to payload, and rechange the protection from read write to read execute. In this, you will not have any difference between the VAD and the current section protection that could limit the detection from EDR solution. The last thing is you have to be careful because the malware should not be larger than the section you are writing on. So if you are writing on the .text sections, which is 4 kilobyte length, and you are writing 50 kilobyte on it, you will have a problem of permission because you will be writing on another section. So what the DR says about it. If you look the process injection with virtual alloc eggs, under the Microsoft Defender for Endpoint, you will see several events, and the two main related to virtual alloc are the anomalous memory allocation, which leads to the detection of process injection. So this is fully related to the use of virtual alloc eggs from a remote process to the creation of a section in the notepad.exe process. With module stomping, we don't have this kind of detection because we are not allocating any memory in the remote process. It's a remote process itself with a load library that is allocating its memory. And moreover, we have some backed memory area on the remote process we can use for our malware. So it's kind of interesting. Just by using the load library instead of the virtual alloc, we are able to bypass some specific events related to the process injection. But this technique is not bulletproof. We are trading one IOC for another because the load library A function still raising some events. These events can be caught, and when caught, the security solution can raise additional detection. So, for example, with Microsoft Defender for Endpoint, we have a specific event related to the use of create remote thread that is caught and lead to the detection of the process injection attempt. So what we have done is kind of nothing. We have traded the virtual alloc IOC for a create remote thread IOC. So the next step is how we can bypass this event and how we can perform our process injection and our DLL injection without the create remote thread. So the create remote thread is a Win32 API that is used to create a new thread on a process and start the thread at a given address. So there are some important point here is that if you are starting a new process in a well-known process, if you are starting new thread in a well-known process, so for example, notepad.exe, that is known to have only one thread, security product can define this behavior and start in raising events. Likewise, if you are looking at the stack thread of each thread, the one started with create remote thread will be started on RTL user thread start, which is an IOC known by a security solution and can be lead to the detection of your process injection attempt. When we are doing process injection, we don't want to create a new thread. We use create remote thread to hijack the execution flow and compel the remote process to start execution at a given address. So the address where we have our payload. So we are using create remote thread because it's simple. It's a built-in function, and we just have to pass the address as an argument, and everything will be okay. But we can find additional way to start execution of our payload. So once our payload is written in our process memory, we can just wait for the process to start executing it by itself. The problem is that the process doesn't even know a new section has been created. It doesn't even know that a code exists on this section. So it would likely never execute this this function. But what we can do is we can help him a little bit. To redirect his execution flow directly on the section we have created. So if we look at the notepad.exe section, memory space, you will see a space related to DLL. So for example, all the code related to ntdl.dll, the code related to notepad.exe, which is in his .text sections, and as always, some free space. So free space that have already been here, or free space we have created with a load library or with virtual alloc. So on the ntdl.dll section, what you will see is all the code related to the Win32 API. So you can choose any Win32 API as long as it is used by the ntdl.dll. And here it's a code cave or the free space, and it will be used to write our payload. What we will do is that our malicious payload, our injector, will start patching the function in the ntdl.dll by modifying one of the instructions, and it will call the address where our payload has been written. So in fact, this call address will replace our create remote thread. And here, our malicious code will do some things before calling our malicious beacon. It will save all the context, so all the register and stack context. It will remove the hook we have placed on the ntdl function. It will call our beacon, and once the beacon has been executed, it will restore the context and return the execution flow to the RTL NT-status function. So for the notepad.exe, when it will try to call the RTL NT-status error function, what happened is that his execution flow will be automatically redirected to our malicious section. And once our malicious section has been executed, it will give back the execution flow to the ntdl function that will end and return the execution flow to the notepad.exe. So at no moment there is any thread involved. We haven't created any thread, and we were able to redirect the execution flow of the function. So if we look at the thread stack, during this execution, you will see that no RTL function are involved, and we have our load library that has been executed without the creation of a new thread. The problem is that we have some kind of broken the thread stack during the call of load library. So you have some random address on it that can be used as an IOC, but that's something that can be fixed given some time. So what does another says about it? When you use create remote thread, as we have seen before, you have directly detection of process injection. When you use this threadless injection technique, in fact, you're not doing anything on the process. You're not compelling him to change his execution flow, or you're just modifying some bytes somewhere. And in fact, Microsoft Defender for Endpoint doesn't detect anything on it. But it's not the best thing, because when we have modified the ntdl.dll file, in fact, we have performed what we call the patch. So we have changed the protection of the ntdl several times, and this led to some minor event on the Microsoft Defender that says that a process changed the protection of a memory region of a specific process. So this event doesn't lead directly to process injection, but they are not really nice. So what we can do to improve this technique is avoid the use of read-write-execute protection on the hooked function. So that's something we need to be able to patch the function on the ntdl, and to be able to rewrite the patch when our payload is called. We can do this with, for example, hardware breakpoints. So it's some extension we can implement to avoid these events. The second point is the unclean thread stack and the shellcode. So we are using some shellcode that will mess with the thread stack, and that it's something we can fix later, given a specific function call. We can play with a stack at the end of the shellcode execution to reset it in a good way. And the last one is EDR hooks. So this technique doesn't take in account the EDR hooks. So if there are any hooks set by the EDR, you will have a detection related to these hooks. But we will see that later. There is another technique I like. It's the goal is the same, is changing the execution flow of a process, but it's based on the Nirvana hook instead of patching. So the Nirvana hook are instrumentation callback defined on Windows, and they are set up between the kernel and the userland. So in a standard way, when a process is doing a syscall, it will send the syscall to the kernel. The kernel will execute the syscall and will send back the return code, so the systhread, to the process. When you are implementing a Nirvana hook, the process will still do the syscall. The kernel will still process the syscall, but it will not send the systhread directly to the notepad.exe, but it will send the systhread to the Nirvana hook, and the Nirvana hook will send back the result to the notepad.exe. So Nirvana hook are a way to have scheduled execution of arbitrary code on any process. To set up a Nirvana hook, we use usually the NTSet process information API, and by reversing this API, we saw that it's possible to set a Nirvana hook on a remote process. So you can just target an arbitrary process on your computer and set a new Nirvana hook on it. The problem is that to target a remote process, you have to have the SEDebug privilege enabled. So basically, you have to be a local administrator on your machine. So this is not a technique you can use every day, but it's more like a post-exploitation technique. A post-exploitation technique you will use once you have a compromised computer and you have to have persistency on any user on the computer. So what you can do here is you will allocate different buffer, one for the Cobalt Strike beacon you want to execute, for example, one for the Nirvana hook you want to be executed. You will write your Nirvana hook and your Cobalt Strike beacon on each section, and you will register the Nirvana hook using the NTSet information process. And when the notepad.exe will do a syscall, any syscall, it will trigger our Nirvana hook and trigger the execution of our Cobalt Strike beacon. For the Nirvana hook code, you have something like this, so it's quite simple. You save all context, and you just call your beacon address. You restore the context, and you jump on the specific R10 registry that contains the address of the calling function. And that's it. So maybe, I don't know if I have time. Do not run my clock. So maybe some demo. So you have here the notepad.exe that is run, the set process injection loader that is run. It's waiting for the hook to be called, so the Nirvana hook to be called. And when it's called, you see that directly you have your beacons that spawn. So it's only work on with the local admin privileges, but for all EDR I used, I saw that NTSet process information is a function that is not really either known or monitored. We can see on Sentinel-1 EDR that it's something known. You have some hook set on it, but it doesn't raise any hard detection on it. Okay. So before I talk about EDR hooks, so how to bypass them. So what's our EDR hook? It's just when you download, when you install a security product, it will come with different DLL, and every time you run a process, the security solution will inject its DLL in the remote process. We'll inject the DLL in the remote process, and we'll start to modify some instruction on the NTDL function, on the NTDL DLL. And every time you are calling a Win32 API, in fact, you are calling a specific code set up by the security product. And this code will just check the different parameter you are using on your Win32 API call, and determine if its call is malicious or not. So, for example, if you are calling, if you are using a create remote thread on a remote process with a specific address that is not known by the system. When the EDR hook will look at your parameter, it will see that you are targeting a remote process on a section not known and with a specific code. So it will likely raise the detection and stop your call. So there are different hooks. There are user land and kernel land hooks. So for everything that is kernel land, we can't do anything about it without specific drivers or vulnerable drivers. But for everything that is in user land, it's something we can change. It's something we can patch. So we can just remove these hooks. Yeah. So the most known technique is by patching. So the EDR is just modifying some instruction at the beginning of different function. So you can just look at the functions that are not equal to the one stored in the DLL file on the file system and rewrite these instructions. But if the security solution is performing integrity checks on these sections, it's something that will be spot on. The other point is that to repatch the EDR hook, you will have to change the memory protection. So you will have to call virtual protect. That is a function that can also be hooked. So in fact, you will be detected just before removing these hooks. So patching is an interesting technique. It's kind of simple, but it might not be the best. What I like, it's using hardware breakpoint. So this is not a unhooking technique. It's a way to bypass the hook, but not to remove the hook. So what we do here is instead of patching and removing the hook, we will set a breakpoint on the syscall instruction. and we will call the function, the hooked function, with random parameters. So, for example, instead of calling a create remote thread on a remote process at a specific address, we call create remote thread on our process with a well-known address. So when the EDR will see this parameter, it will think it's just a standard thread creation and will allow the code to be executed. And right before giving hand to the kernel with the syscall, you will replace dynamically the code, the argument in the stack. So the kernel will have the malicious arguments. So you have your malicious process that want to call specific Win32 API. What you will do is you will define a breakpoint. You will say that every time the syscall instruction is called, you will raise a debugging event. You will set a breakpoint handler. So this breakpoint handler is just something that will catch the breakpoint event and perform some action during this event. And you will call your malicious function. So, for example, here ntprotect with random arguments. So, for example, everything null. For the breakpoint handler, will patch the argument in the stack. So it will just set some register and set some stack space in order to recreate the arguments directly on the stack. When you will call the ntprotect with false argument, you will pass the EDR hook. Because your arguments are not malicious, the EDR will not see anything. You will arrive to the syscall instruction that will raise a debugging event. The breakpoint handler will catch this debug event, will patch all your malicious arguments directly on the register and on the stack, and will give back the hand to the ntprotect virtual memory function that will finalize his syscall, give the malicious parameter to the kernel, and the EDR hook didn't know anything about. The problem is that if you have any EDR hook at the kernel level, you are not bypassing anything. You are just bypassing here userland hooks. So yeah, that's kind of all. I don't know if you have any question. If there are some parts you would like to dive into.
I know that Microsoft tried to stop EDR solution, but do kernel hook because of some of them cause blue screen of death, for example. Do you know some other solution that actually do kernel hook? And if yes, do you know any solution to bypass it? To bypass it as a non-administrator?
Today it's quite hard to do a kernel hook because of some security solutions set up by Microsoft that will do some integrity check on a specific kernel structure, and if it shows some differences, it will just blue screen. So I don't think some EDR solution are trying today to do some kernel hook, but they have some additional tools that can be related to kernel hook, which is a kernel callback. So they can register to specific kernel events, and they can act before the kernel performs the malicious actions. So all all Win32 API are not eligible to kernel callback because it's time consuming and resource consuming, but the main one can be registered and protected.
Okay, thank you. And do you know how to bypass kernel hooks as a non-admin?
As a non-admin, I don't know. Usually you have to, if you want to interact with the kernel, you have to be at the kernel level. So you have to exploit some driver. So, you can find some, vulnerabilities that allows, the deployment of unsigned driver, for example, or exploiting driver, vulnerable drivers. For the deployment of unsigned driver, I don't have any vulnerability to present here. But for the exploitation of a vulnerable driver, you have a lot of codes that exploit it.
Okay, thank you.
A good example about it is EDR Sandblast project that remove all kernel callback defined on the specific process and allow to get a CMD without any kernel callback related to it.
Okay, thank you.
Thank you very much. Also have a question about using callbacks instead of calls. What is your experience with it, with using callbacks to call your malicious code?
I'm not sure to understand the question.
So instead of creating remote thread, just jump to your malicious code using callback functions.
It's usually better because when you use a create remote thread, the execution flow is modified from a remote process. So it's a remote process that asks the targeted process to modify its execution flow. With a callback function, instrumentation callback, or other kind of callback, it's a remote process. It's a targeted process that modifies its execution flows by itself. So yes, you set up everything from a remote process, but in fact, when it will change its execution flow, it's not something happening from the outside of the process. It's a process that says, oh, something has been registered here, so I will just jump on it. It's something on my memory space. I just register it, and I don't remember. But yeah, it's usually better. After, when you are registering this callback, you have to write all your code directly on the process. So you will have to create additional space. You will have to write something on it. So in fact, it's like always you are trading some IOCs for other. You are trading the create remote thread IOC for some memory allocation in the process.
Thank you.
You're welcome.
Thank you for the talk. Yeah. You said you took inspiration from what you've seen in malware. So I was wondering, have you actually observed in the wild some malware that were really aware of the EDR and really like patching it or doing hardware breakpoints like you described? Or, and if not, what is the most advanced technique for process injection that you have seen really used in the wild? I
didn't do any malware inspection. I'm not a malware. I don't do any malware reversing. So I don't really know what you can see in the wild. I read some articles, but I didn't see some from my eyes. Yeah.
What is your preferred language to do malware development, and why this language?
I use C for malware development. I use it because it's the easiest to talk with Win32 API. When you are injecting raw shellcode or raw assembly, I find it more easier to deal with these instructions. After, whatever your language, you have some pros and cons. If you're using Python, you will have some more important executable file, but Python by itself is doing a lot of shady things by default, so it's a process that can be less seen by EDR. We saw some Java malware because of the JVM that is hiding all the malicious stuff that is performed by the code. So you have some pros and cons. It's depend on your use case, and yeah, everything is good as long as it works.
Thank you.
You're welcome. So I kind of forget to do my conclusion. In fact, what I like in these techniques is that it's not something new or something that exploits a deep vulnerability. It's something that anyone can see. It's just using some APIs that exist. It's sometimes you don't have to just add a different layer of obfuscation on your malware to make it work. You just have to take a step back and see what your operating system is giving you as a tool, and try to find some edge case you can use at your advantage, and you can hijack to bypass the security solution. The security solution today, it's I think a kind of a hard job, because you have to see everything. You have to be you have to implement something secure, but that doesn't use a lot of resources, because otherwise the computer will not be able to work. So you can always find a window where you can shoot, as long as it's not something well known, as long as it's something new. So, yeah.
Thanks. Just a quick step back. If the process injection is so commonly detected, is there a reason to not actually use it, and besides just trying to hide yourself in other process? Like, what are the other considerations here, pros and cons of doing process injection and not doing process injection, and just running in your own thread?
When you do process injection, I think it's kind of interesting, because it allows you to leave the current context you are in. So, for example, you are doing a phishing campaign with a maldoc. You don't want to step on as a child of winword.exe. You want to be in a more interesting process with less detections, where you can do more things. So in this case, I think process injection is interesting. But if you have a remote access to a computer, and you have a tool you want to execute, and it's something it's not really detected by a security solution, process injection is not useful. You don't want to hijack the execution flow of a process. You don't want to hijack the identity of a process. You just want to run your tool. So just double click on your executable file, and you will have the same result. Process injection, when you do process injection, you take a risk, because the Win32 API you are using, or the technique you are using, can be detected at any moment. Once you are injected on your process, the fact that you have a malicious payload injected on a process can trigger security solution scanning. So it's not something you want to be on. For me, it's a last solution. And when you have to have something specific on a specific situation.
So I think we are done for this talk. Thank you.
Yeah, thank you.